Hello everyone, and welcome to Elec3300 Advanced Linear Electronics online version. I just wanted to give you a heads up that this part that we're talking about, section 7.4 in our textbook, and this is only part one of maybe a couple other parts that we'll be doing in video. We'll be conducting an ABET assessment, so you can come back and look at these. We're going to do outcome 1 and 5. For this section. So when you're introducing the 555 IC, it has a number of useful functions. It provides a variety of outputs that we'll be discussing. And the name 555 comes from these three resistors that are here, 5K ohm resistors that are in the circuit. That's internal within the 555. And really, by the way, there are around 28 transistors internal. And what we're showing here is just a functional block diagram inside that 555. Here's the pinout that you can stop the video and look at it for reference. A couple things to take note is VCC is pin 8 and ground is pin 1, which is usually not the case. For ground anyway, and the output's pin 3, so always set up the ground and VCC as you start to build your circuit, because a lot of students forget to do that. They start building the circuit and forget about power and ground. Won't work without it, and you know that. So there's three main operating configurations with the 555. I've listed them here, but we're going to concentrate on this video with the monostable mode. So we're going to set it up that way. And a couple of things that we can do in this mode is set up a pulse width modulation. And some students have used it as a debouncing method for switches in some of their senior projects. And we'll see how this works as we build this circuit. Here's an overview of how the monostable configuration operates. Basically, we're going to have a trigger that will be going to pin 2 of the integrated circuit, and this is normally high, but when it goes low and comes back high, it's going to initiate an output. We're going to use some traditional timing methods. We're going to just use an RC configuration, and the output is the opposite. It's normally low, but it'll go high for a specific length of time, and this is what the output will look like. It'll be low normally, go high for a specific amount of time, and that's dependent on this algorithm, 1.1 times R1 times C1. And this output is on pin 3 of the 555. So here is a setup of external resistors R1 and R2, as well as 2 capacitors. R1 and C1 are the main RC network that we're going to use for precision timing for our circuit. And notice that the trigger pulse is normally high at pin 2, so it's normally high. And there's our input there, the trigger pulse at pin 2. When it goes low momentarily, it sets off the process of charging C1. And it'll charge up to about 2/3 of whatever you're supplying for VCC. And then it just discharges quickly. Notice that your VCC can be 5 volts to 15. I've even seen the data sheets, they'll go up to 18 volts, but that's the normal operating voltage there. So how does the charging and discharging occur? It has to do with the internal function of the IC, if we take a look at that. The low pulse trigger at pin 2 sets a flip-flop internal in the 555. And what that does, it actually turns off that NPN transistor that's internal. And what that does is that opens up pin 7, because it's normally, when it's on, it's connected to ground. But when it opens that up, that's when we can do our charging. So when the transistor is off, there's no ground at pin 7, the capacitor C1 charges. And this action of charging C1 provides a pulse as a one-shot to the output pin 7. Once C1 discharges, the flip-flop resets and the circuit reverts back to turning the transistor on, and that will ground pin 7, which provides ground there, and really short circuits prevents C1 from charging at that point. And now at that point it'll wait for the next pulse and it'll start that process over again. So let's look at example 1. If we're given C1 is equal to 10 microfarad, and always remember the C2 is always a 0.01 microfarad. That's a common value that's used. And R2 is just a value as a current limiting resistor with our switch that we're using right now, the momentary switch. So those aren't the important items. The 10 microfarad is the timing capacitor, and then R1 is the other part of that network of the RC network. So we want to have a 5.5 second output pulse, and so we want to determine R1. So we're going to rearrange our formula, and if we do everything correctly with 0.5 seconds divided by 1.1 times 10 microfarad, we get a value of 45.5 K. So I did build that circuit, and I'd like you to go ahead and build that circuit, test it out, and you can learn more about what we've been discussing in the monostable configuration. Notice I changed the color of my oscilloscope signals so I could measure that more accurately. I have some ideas for you how to set up your oscilloscope, but I'd like you to use it. If you're using multisim, use the LM555CM IC that you could search for and grab that. That way we're all doing something the same. Here's some tips, and I'll just go over them. If you're going to have some long delays, you have to remember that the tolerances of the capacitors are around 20%, so they're more inaccurate. So you would like to have a higher value of the resistor rather than a higher value of capacitor. So think about your timing that you want. It's an RC network times 1.1. Go with a bigger size resistor rather than a bigger size capacitor when you have to choose between them. And if you're going to be switching different values, you want to start off with something small. I'll show you what I mean on the next page here. So here is an interesting way to set up your monostable with different values of pulses, and by switching between these. So in this situation I'm using a smaller cap, and I have a range of 1K to 1 mega ohm in my resistor selection. Now if you need more horsepower to drive some components for your output pin 3, you have to remember that approximately 200 milliamps is about the maximum that you can drive in that circuit. So you might have to have something external to drive relays. This is okay for driving LEDs and other small things, but if you want to drive something like a relay, then you need an external circuit. Here's a couple examples. And for these transistors, you could use a tip 31 for an MPN or a tip 32 for a PNP. Look up the data sheets for those transistors, see if it works for your situation. But if you're powering something like a motor, an LED or whatever it is you're doing, and you can use a diode to absorb any inductive recoil as well. So there's a couple ideas for sourcing and syncing. So I'd like you to do problems 733 and 735 and have that completed by March 31st. See you later. Have a good day.